London Machine Learning Meetup. London Machine Learning Meetup. London Machine Learning Meetup. London Machine Learning
Well, I was just saying that personally I've always been very interested in how machine learning crosses over into the real, the physical, the tangible world. And so I'm very happy this month we've got two speakers who've taken time out of their busy schedule to talk about machine learning and how that crosses over into robotics. The first we'll have Ingmar Posner, who's been working with the Oxford Mobile Robotics Group, and particularly with a recent spin-out company, Oxbotica, who does self-driving cars, and talk about maybe some of, I guess, the philosophy around the approach to learning in uncertain environments. So, no further ado, thank you to Ingmar.
Thanks, Dirk. Okay, so I'm going to do the microphone thing. If you can't hear me in the back, just wave, okay? Usually, you can just about hear it. Just about hear it, yeah? Is that okay?
If you're a little bit louder, it'd be good.
Okay, a little bit louder. All right. I tend to make this a bit interactive, so this is a pretty big group, so we may have to wait till the end with questions, but if you feel you have a pressing question, please, by all means, shout out, give me a sign, and we can make this more of a conversation. That's usually a really, really important thing for me. Now, it's a real pleasure to be here, and today I'd like to talk about learning on the job, which sounds a little bit weird, particularly when we talk about machine learning and robotics and, oh, that's better, okay. Machine learning and robotics and autonomous driving. Whoa, crazy sound effects. But let me take you through it, and hopefully I can take you along on a little bit of the journey of the philosophy that we in Oxford have when developing self-driving vehicles, which is not the only thing we're about, but I'll get to that. All right, so if you ask me now, today, what probably the thing is that I'm most excited about, it's this thing here. So this is the LUTS project. Has anybody here heard of LUTS? Pods in Milton Keynes. Anyone? Yeah, a couple of people? All right, okay. So the idea is that there's going to be 3 prototype pods, these guys, that will shuttle people in Milton Keynes from sort of the shopping center to the train station and back autonomously. And the whole thing is going to get scaled up to sort of a 40-pod PRT system in a thing called UK Autodrive. Okay, so that's sort of the next step. And that's exciting because these things do not run on the road. Okay, so they do not run on the road, but you know, autonomous cars and stuff is kind of the exciting thing. So how does that fit in? It's actually the evolution of this guy. This guy here is the Oxford RobotCar. The Oxford RobotCar was the very first, and still is actually, the very first and only self-driving car in the UK. The group, the Oxford Mobile Robotics Group, Paul and I launched this in late 2011, early 2012, where we did a pretty unusual thing for a research group, which basically was take everybody offline, everybody puts pens down, nobody writes any papers, and just do some systems engineering. So we went to a Nissan dealership, went to the forecourt, picked up one of those Nissan Leafs, and said to the group, 4 months from now, we're going to invite the press, and this guy's going to drive itself. Okay, so a little bit of consternation there, but we did manage to do it. Now, at the time, one interesting thing was that it was very much about the navigation aspect of it. So in early 2012, it was very much about where are you, or where am I, in terms of a machine. It was less about the perception, but a lot of that stuff is now come. A lot of that stuff is now coming over the past couple of years as well. And so the next iteration of that is really about putting this sort of technology into the real world, into an environment that is low impact, very important, low impact. So if something goes wrong, doesn't mean anything bad necessarily happens, but that allows us to get 24/7 exposure for months. Really, really important. If we want to figure out how well this technology performs, if we want to figure out where it fails, when it fails, what the corner cases are, then by all means, we need to have it out there all the time. Now, this sort of long-term deployment brings a whole bunch of challenges, right? And we'll talk about some of them, or I'll talk about some of them during the course of the next, I don't know, 45, 50 minutes. All right. What does this whole thing come to? One thing that Dirk will know all about is called the Selenium system, which is basically a pretty amazing software stack that does bottom-up, bottom-to-top integration of you pick your sensors, and it will go all the way up through navigation, perception, planning and control, all the way up to the smartphone application that actually allows you to summon your vehicle. And that's really, really important for us. And the whole thing is interacted with via an iPad. That's the whole thing. So you just stick an iPad into your vehicle, and all the driver ever sees is this guy there, where the driver has to go through a sort of short but fairly rigorous, so fairly obvious handover sequence. The vehicle will then offer autonomy, and we can pause for a second here. It will offer autonomy, very important, and then you're good to go. And so this thing you're going to find in Lutz and Autodrive, as I've mentioned. This thing you will find in the Gateway project, which is also something very similar to the pods in Milton Keynes, just different pods in different cities. So this was actually happening right here in London, in Greenwich. We have this sort of system in a variety of different sort of automotive trials. Okay, so interesting thing about Selenium is that it does basically the whole stack, and for each one of those things we have different sensors that we can work with. So we can do mapping and navigation and perception with vision, and we can do mapping, navigation, and perception with laser, and then we do planning, control, safety, interfaces, integration and testing frameworks. And with 45-50 minutes, I don't really have time to speak about much of this, but I'll touch on as much as I possibly can, mainly in sort of the mapping, navigation, and the perception side. First of all, though, why do we bother with this? What's the driverless cars? What's that about? So we're known for not being bold ever in Oxford, and therefore we got up about 4 years ago and said transport is pretty much broken. And I can say that with extreme vigor now, as I was pretty much on the last train out of Oxford when all sort of signal hell broke loose just outside Oxford. So I just about made it here together with Dirk. But the idea is that we're not really condemned to a future of congestion. Okay, there's something we can do about this, and we firmly believe that modern robotics lies at the heart of a solution of this. Okay, and there are a couple of things that we think about when we deal with this. So first of all, we think about whether I must always be in control. Clearly, I don't think so, because otherwise I wouldn't be standing here giving this talk. Why can't I email or Skype or program, yay, or negotiate? Okay, or think when I'm in a traffic jam? Are the roads really full? So the answer to that is probably not. There's a study that says the current road network is probably under capacity by a factor of 2 to 3 times, right? So that's pretty substantial, given that certainly up in Oxford, we're in a traffic jam on the A34 basically every morning. If you've ever been on the M25, it's probably the biggest parking convention ever envisioned, right? Can only the able drive? Now that's a big deal. What does it mean to be able to drive? So my mum, bless her, really doesn't like driving in the dark. That's not because she's a bad driver. She just doesn't like it. She doesn't feel like she she perceives her environment well enough to do this. That said, a lot of the technology that I can talk about here will actually directly feed into this in terms of driver systems, and that's a big deal. What does it mean to be able to drive? And I think just from that point of view, it's well worth at least looking at this sort of tech and seeing how we can push the boundaries of us redefining what that means. And here's another interesting question. Why are we even insuring against human error? So there are some people that believe that there will be a time when, looking back, it will be nuts to have thought that humans were ever in control of cars. Okay? Exactly when that time comes, which is usually the question that comes next, we can talk about. Okay? But why are we insuring against human error? So I'll outline a little bit about what our vision is in terms of what an autonomous car does in this sort of circumstance and how these sort of things fit in. But what it boils down to is that we're all short in time, and mainly apart from me, we're all pretty bad at driving. Okay? But the story is much bigger than just the tech. So I'm a technology enthusiast, and I really care about getting this sort of tech out there. But really it's about safety, and it's about access, it's about efficiency, and really it's about quality of life. We want to get some of those minutes and hours back. Really though, again, as a technology enthusiast, that also means that it's not just about the technology, but it's also about policy, and it's also about society. And trust is a really big deal. Okay? Who here has got cruise control in their cars? Okay, who here uses it? Okay, I suspect you use it and you're quite comfortable using it because lots of people around you have also used it and your friends have used it and they said, it's really great and it really works, right? But that means you've built a model of trust, how you can interact with this technology, that you can rely on it while it's doing what you ask it to do, and that's a good thing. Now, who here, if I told you that outside there's an autonomous car with no steering wheel but a microwave, right, which is clearly everybody assuming that an autonomous car has no control inputs other than a sofa of some shape, who here would get into an autonomous car and let it drive you to the airport from here, right now? Excellent. Okay, so I've been asking this question for basically regularly for about 4 years, and in the beginning there was just complete silence, and now I've seen about a dozen hands. That's a pretty big deal. Now, the question that I would hopefully expect in return is, what can you tell me about the autonomous car? How is it being prepped? What does it know about the environment? Right? Because that's really a pretty big difference between this idea of getting autonomy on demand in any weather condition to whatever place, from whatever place, and this idea that actually there is a world where the technology can decide whether it knows enough about the world to drive you places. Okay? And that's really, really important. Okay, so a couple of things that we're going to do. Let the cars drive, duh. Let the cars get better at driving over time. That's important. That's really important. And even more important, let the cars decide when they can drive. Okay. What that boils down to then is that in this world that I'm kind of starting to spin up here, we talk about driving some of the people to some of the places some of the time. And that's a pretty special sort of thing. So imagine this. You're going to go and you're going to buy yourself a new car. So you're going to go to the dealer and you will go onto the forecourt and you will pay a little bit extra for the autonomy pack, right? Which is basically of the order of the price that you would pay for seat heating, hopefully, right? Not 200K, but, you know, much less, much less. And you will drive this car off the forecourt and the car will know how to do exactly no things, which sounds a bit disappointing, right? But then you're going to go through the routines that most of our lives have. You're going to drive to work, you're going to drive the kids to school, you're going to go shopping, you're going to go and visit grandma, you're going to do all of those things, and you do them a lot, because that's what our lives sadly look like very often. And one day, when you're stuck on the M25 in some traffic jam, a light will come on your dashboard, and that will mean, hey, you know what, I can drive you for the next 126 meters, if you like, because I know exactly where I am. And I've seen this world so often, right? I've seen it when the sun shines and when it rains and when it's snowing and when it's overcast and all of those different faces of the world, because you've driven through here many, many times. And I'm pretty sure I know where I am and what the world looks like. And if you want to, if you accept this, then, by the way, your insurance premium is going to go down. Okay. Now that is interesting. That is notably different from getting into a car with no steering wheel and saying, I would right now like to be driven to this place. Go. Okay. Why is it interesting? Because this last bit is really, really, really hard, whereas the first bit learns from the driver in the loop. Okay. And that is really important. So in a way, that is that is somewhat different from the next talk. I also very much talk about learning from demonstration. Okay, but in the wider sort of sense. The other interesting thing about that is that all of a sudden you can see this sort of idea of a viable business model around this, right? Because all of a sudden when you talk about experiencing the world until it's good for you to drive, until the car says, hey, I know enough about the world to drive you, and we'll again talk about how that looks in tech in a minute, then all of a sudden you can imagine car manufacturers competing like they do today on fuel efficiency, competing on things like miles driven autonomously for miles driven training, right? And you can even imagine that these experiences get shared between cars. So just because you've never driven to Edinburgh doesn't mean nobody else has, right? And suddenly we're kind of in this service provision world that car manufacturers find very attractive, because no longer will they be the people who just bend metal, okay? And they know this. Okay, so what does that mean? Well, let's start with sort of the four pillars of what we're talking about here. One is, what does the world look like? So mapping, surveying. The next one's going to be localization. Where am I? And then we're going to talk about perception. And I doubt we'll have the time to actually talk about anything related to planning, but we'll see how we go. So low-cost survey. What does the world look like? Bit of a substrate. So here's a thing that we use all the time. So this guy here is a stereo camera. So two cameras here, we know what the baseline is. All of this stuff is sort of COTS, off-the-shelf components. And what we have here are the two frames, one from each camera. They're slightly offset. Because we know the baseline, we can find interesting things in each camera, correlate them across, and we can know where they are in 3D. And that's helpful because that tells us something about scale. Now, not only do we correlate them across like this, we also correlate them through time. And that is helpful because all of a sudden we can figure out how we're moving. And by we, I actually mean that camera. Okay, so this is basically, it's called visual odometry, and allows us a fairly accurate way of estimating ego motion going through the world. Okay, it's also interesting because that particular piece of software just got licensed to go to Mars on the ExoMars missions, if ever they will happen. But that was an exciting moment. Okay, so that tells us fairly accurately how we move through the world. If you now imagine you take one of those cameras and you stick it on a car under a taxi cab here, and you bolt something else to the same car, like for example a laser down here, and you do some pretty intricate calibration, not just spatially, which everybody does, but also in terms of time, which hardly anybody does. Okay, temporal synchronization here, really, really important. Then because you know how the camera is moving, you know how the laser is moving, right? And so what you can do is you can take one of these 2D lasers, which is very important because it's really, really cheap, right, compared to the old systems. You can take one of these 2D lasers, which is kind of casting laser light, kind of a curtain of laser light through the world like this. And so in case you don't quite know what a laser scanner is, imagine one of these laser pointers, right, that basically gets range and reflectance, like 500 different angles, about 50 times a second. Okay, lots and lots of these measurements. And because you control this thing through space like this, you can drive through London and you come up with a representation like this, which is basically a centimeter accurate survey of what London looks like. Important thing, there was no stopping here. So this sort of stuff was recorded at traffic speed. Okay, so there's no stopping, getting out, building up a total station, spending 180 grand on a scanner. This whole system that builds those maps is of the order of 3.5K. And that's the data so that's what the camera sees when it looks out the back and kind of construct these models. And often people ask me how we know that these models are in any way useful or good. And the answer in this particular case is you can look at the lane markings, right, and see how well they're lined up. Another thing I should stress is this whole system does not use any GPS at all. So it's entirely infrastructure free, onboard sensing only. What that means, very nicely, is that it works indoors as well as outdoors. Okay, and that's going to be a special thing later on. Okay, so this is actually pretty underwhelming now. You would have probably seen a lot of this stuff before, or something like this before. And this is about 4 years old. If we went back to the LUTS project and see what kind of scene priors, or maps in this case, the LUTS pods build as they just drive through Milton Keynes twice every month, that now very much looks like this, right? So what we've got here is a 3D model of the world, colored by the colors of the camera. And we can do that, of course, because we've got these calibrations, right? So we can project the laser into the camera and we can see what kind of color that point should have, and we project that back into 3D. Okay, so I have a pretty good idea of what the world looks like in 3D, and that pretty cheaply. Previously, we've talked about laser points. There's some people out there, believe it or not, that much rather would have a dense reconstruction of the world. Okay, so not just individual points, but something like a continuously queryable surface, right? So at every point, you can click on a thing and say, this is this far away from that, etc., etc. And that's actually also something that we can do as here in a third-party data set from the Kitty benchmarks. Does anybody here know the Kitty benchmark?
London Machine Learning Meetup.
Okay. It's basically a benchmark of data, lots of data for things like autonomous driving. So you can do things like object detection, tracking, etc., etc. It's worth looking at. Lots of data if you want to play with it. Okay. So given that we have one of these models, or n of these models, and we can call them anything, by the way. I've called them maps. I've called them surveys. In not too long, I'm going to call them experience. And don't get hung up on the fact that this is actually a 3D model or a video sequence or whatever it is. We'll get to that bit. How can I leverage this stuff to actually find out where I am? Because, if you're an autonomous car, this is something you really, really want to know. Okay, so let's get back to the system. And I'm going to talk about a couple of ways of how we do this, how the robot car does this. The same video that we've just seen. So again, we've got this planar LiDAR that kind of casts this curtain of laser light, all very Doctor Who. And what that means is that actually, because we've just seen that you can build up this enormous nice map of the world, you could do the same thing locally, right? So you can imagine that you've got this map of the world, and now you drive through the same place again, and you build up a very local picture of what the world looks like, right? And what you can do then is take this local picture of the world here, again, without GPS and without inertial, which means it's cheap. This is a good thing. And you can basically take that local picture, project it down to the ground, build a 2D histogram. This is your map. This is the thing that you're trying to match, and match it. So you have this 3D information. You record it in 3D, but you match it in 2D, which makes it really quite fast. Very, very fast indeed. Now, this is a bit of an older system, so we now kind of moved on to something slightly different. But in essence, this sort of thing fared us really, really well because it's really fast. And the question, of course, is how accurate is it? Now, we need to pause for a second here. It's really quite hard to figure out how well you are localized in the real world, because if I could do that really, really, really well, I either have to spend a lot of money or I've solved my problem in some other way. I've engineered it away, right? So ground truth in the real world about localization, difficult thing. So one thing that we do is we look at this idea of consistency, right? So in this particular case, we spend £100,000 on a really, really, really good inertial navigation system. So that means it's a system that incorporates GPS measurements as well as sort of inertial measurements, right? And we don't use it to navigate, because that would be foolish, but we want to see how well we can replicate our path as we drive around the same loop over and over and over again, okay? So this guy here is the loop that we drove about 50 times or so. And if you drive in the same lane of a very, very narrow street, what you would hope is that ideally those traces that you record with your INS lie exactly on top of each other, right? Clearly that's not going to be the case because there's going to be a little bit of noise in there, a little bit of variation. So you'll get a band, but you would like that band to be really, really quite thin, okay? And that band that comes from the really expensive INS is the gray lines, which you can hopefully just about see under here, right? And so we can see that the gray lines really go nuts around about here, right? So you kind of see something branching off here and branching off there, and it gets pretty wide. And so we call this part the corner of doom. What's going on in the corner of doom? Anybody got any ideas? Yeah, okay, somebody set it up here.
GPS reflections from a building or something?
Right, so it's not reflections, somebody set it up here, it's trees. Can't remember who said it, but it's exactly right. Point for you. It's exactly right. You get trees, overhanging trees. And of course, that makes other approaches also tricky, but we'll talk about that in a second. But getting a good GPS signal that is usable, even with something that will cost you 100 grand, is really, really quite hard. In fact, I walked here from the train station with a GPS in my phone, and I got lost like 4 times. Why? Because actually, I'm just walking along amidst lots and lots of buildings, right? So you get all sorts of noise effects and there are all sorts of drift. Personally, I wouldn't want to sit in an autonomous car driven by the grey thing, particularly not around a roundabout. But hey, or ever for that matter. The good news is that if we take the system I've just described, where we literally just local matching, what we get is the red line. Okay, so 2 interesting things here. Clearly, if we look at the corner of doom, we're pretty consistent throughout here, and that makes sense because we're only using onboard sensing, so no GPS problems, right? The other thing is that as you go around the length here, very often you find it's more consistent, i.e. more narrow, than the grey thing, and that was really, really encouraging. So it really is quite accurate. It's more accurate than 100K INS. Okay, so that was a success. But it's still 4.5K, 3.5, 4K. Okay, so that's more than seat heating. We don't like that. We would like to bring it down to something like seat heating. So can we make this cheaper in any way? And the answer is yes, if we did it vision-based. Okay, and the beginnings of this are really quite promising, and hopefully to a lot of you, you will just go, yeah, well, that makes perfect sense. You know, this is how everybody would do it. In fact, this is how everybody did do it. So on one hand, and this, by the way, is another experience or another map, but here you've got your memory. So you just record a video sequence, forget 3D, this is just a video sequence. And on this view, you've got the live view of what the car sees right now. And you pull exactly the same trick as the one that I've just described for the visual odometry, exactly the same thing. Okay, you just match frames across into your memory. And because you can do that, you can tell where you've been in your sort of visual memory. Okay, and that works really well if you have recorded your visual memory a few minutes before you do your sort of repeat run, your localization run, okay? Because typically what happens is that sometimes the world looks like this. And by the way, when people talk about whether autonomous cars work in snow, all of our testing before the 2012 launch was in blizzard conditions, right? So that's what the world looked like back then. And this is the same track in the sun, happens rarely, but it's true. And then we get the same thing when it's overcast, right? It kind of looks different. And then when it's wet, it looks really, really different. And also, if you look at where the trees are and when you do get the sun, lots and lots of things change because the shadows change all the time, right? Now, we thought that is pretty bad for localization. That made us very sad until a student came along called Winston Churchill. I kid you not. His supervisor was Paul Newman. That worked well. And this is not a joke, seriously. I'm going to change my name to Bergman. So he came along and he said, you know what? Why don't we record everything? Let me tell you how this usually goes wrong, right? So typically what would happen is now somebody would come along, like a machine learner, would come along and go, we are going to build a model. Well, hey, we're building a model and we are going to record all this data and then we're going to build a model about what the world looks like, and we're going to perform some inference on that model about how rain will affect my view of the world, how snow will affect my view of the world, how sun will affect my view of the world. And typically those models are quite complex, right? Which means that inference in those models is going to be an approximation, right? And even besides the approximation, you now have to write down a whole bunch of things that you want to somehow perform inference for, right? And all of a sudden it becomes really quite cumbersome. And often it blows up because of the combinatorial explosion. There's so many things you have to write down, most of which you will forget anyway, because the world is complex. And your inference will never be quite right, and there will always be some form of drift in it. So when Winston came and said, we'll just record everything, after laughing him out of the room, we thought, hold on, that is actually not a dumb idea at all. And it turned out he did it. So he went away, and he said, I'm going to go for 3 months initially, for three times a week, 3 times a day, for 3 months he went out and recorded data around the same loop. And so this is kind of just an idea of how the same place varies in different weather conditions and different times of day, right? And the idea there is that you say, okay, well, we have a system which localizes, right? And this guy says, yes, I know where I am with respect to what you've recorded previously. And we also have this VO system. And you can imagine a world where it is mainly red and yellow, okay? And you happen to have a yellow experience and a red experience. And all of that works fine. So this visual odometry trace that tells you how you've moved through the world, you just forget. I don't need it, okay? Because I know exactly where I am. And then something green comes up in your world, but the yellow thing's kind of disappeared. And please don't talk to me about mixing colors, because that confuses the hell out of me. Something green shows up, and you lose localization against the yellow experience, but you're still okay with red. And imagine there's a parameter in your system, one parameter that says you need to always be localized against, in this case, 2 experiences. Okay? Could be 10, could be 15, but just something that gives you comfort that you always kind of know where you are. All right? So at this point, the system goes, crap. Okay, so I've lost my yellow. I have no idea where I am in my yellow experience. So I better hand back autonomy and say I can't drive myself here because I don't know where I am other than in one experience, which violates your constraint of 2 experiences. And I'm going to record where I am. I'm just going to press record on the data that I've got. And lo and behold, I'm actually laying down a new green experience. And when that is done, and I get back to my sort of safe yellow and red world, all is good. I can forget my VO and I'm relocalizing my yellow one and my red one. Okay? And that's kind of how that system works. Note that it actually tells you when it can't drive itself. Interesting, right? It knows when it's lost, when it doesn't quite know where it is, according to your specification of comfort. And so Winston went out and he recorded lots and lots of data, and the answer, as it turns out, is about 33. Yep, that's it, 33. We're done. So what that means is that this guy here is color-coded according to how many experiences you needed until you never got lost. Okay? Interestingly, it gets really, really tricky only about here. And for those of you in the back who can't see the sort of satellite photo overlaid, that's the corner of doom, right? That's the trees. And that's where shadows really kind of confuse you, and that's where the wet really confuses you. Whereas over here, nothing's going on. It's a really, really boring road, and now we've got scientific evidence for that. Right? So there's only kind of a couple of experiences that you need in order to never get lost here. Okay, so that was back in 2012, and that was a pretty big success for Paul and Winston. So Paul got another student called Chris Liniger, and said, please go and record this for hundreds of kilometers. There's your bike, which is what you see him doing here. And he did this for 600 kilometers or something. And that worked pretty well. So he kind of went out cycling lots and lots and lots. And what you see here are the different experiences that you're localizing against. And what you're seeing here is sort of the topological experience graph that's being built up. And when that worked really, really well, they decided to say, okay, well, let's now try this with 1,000 kilometers. And we were kind. We gave him a car, which happens up here, right? So he didn't have to bike all the way. And then we decided that we really want to push this system further, and we just want to dump it into different environments, right? So this is called experience-based navigation. Here we run it in a warehouse, and it works. Here we run it in the Atacama Desert, in a Mars-like environment. That works. Here we run it in an off-road environment. That kind of works. So this sort of tech really, really really transfers into lots of different domains. And for my group, that's a really important thing. Okay, because that sort of technology is not just about autonomous driving, but we may hopefully get there by the time I'm done. All right. So, interesting fact. So we've already talked about. Hold on. Okay. So we've already talked about. Changing weather conditions and dealing with change. And this experience-based navigation idea is really, really neat when you have gradual change, right? So if you want to go out, and you could go out, from morning to evening, and then all through the night and so on, and you recorded data frequently enough, you would actually build an experience graph that goes all the way through, which is neat. But what happens if you don't have that? What happens if there's a lot of change that you want to capture? Like, for example, going from this to something like this to something like this. Does anybody here have experience with point features and machine vision? No. Okay. Right. Do you remember the thing that I talked about with the visual odometry? So we had these points that we found in images. They were kind of small things that we kind of somehow thought were interesting, and we matched them across. Right? That's a very common thing in machine vision. It's a very local thing, because you're basically looking at corners, tiny little corners. Okay, and then you try to describe them somehow. But in order to do this sort of change, in order to model this, it turns out that these point features aren't really enough. What you really need to do is look at regions in the image, okay? And it's only a small step from going from something like this to something like, ooh, there's a tree, or ooh, there's the spire of a church, something that we have some form of semantic association with, but for the machine that isn't necessarily true. Nevertheless, they're image patches, okay? So one thing that you can do here, that these guys did, was learn patches of images where things become suddenly very discriminative, right? So things like individual trees, things like parts of buildings, silhouettes, that sort of stuff. But the important thing here is really what you end up with is something that's place dependent. It's a place dependent feature detector, and that's a really useful thing, because what we're doing here is we're embedding, or rather, we have our machines embed themselves into the workspace they're operating in. And this is what it looks like. Interestingly, it lets you localize across from something like this to something like this, which is unheard of with point features. So that's a pretty powerful idea. Okay, so teach and repeat is the thing that I've just talked about. If you basically go back to this bit here, one thing that we're very close to now is something like learning a feature representation that is place dependent. Okay. And when we talk about that, we're very swiftly into this idea of deep learning, when we learn feature representations and do all sorts of other things, mainly function approximation, which is a very, very powerful idea, very old idea, but deep networks are very, very good at it. And if you now showed the same sort of data, the same sort of idea to a deep network and said, please drive, in this sense, the same route that the human drives, don't get upset about other cars or anything, just learn that at this particular corner you want to turn that way, then what you end up with is this. We don't really have much time to talk about that, but that is one way of doing that sort of thing with a deep network. Okay, but let's talk about perception. What's around me? And actually, the thing I really want you to take away from what I've said so far is this sort of idea of experience-based navigation. Okay, gets better through use. Very important. This is frustrating. Okay. Okay, so because we do autonomous driving, we clearly have the ability to do a whole bunch of object detection, both in 3D and in 2D, because we work in those sort of modalities. And rather than give you a long catalog of what we can do, which I will do briefly, I really want to get back to how the experience paradigm works in this sort of direction. So one thing that's actually a very hard thing to do is sort of generic object detection in 3D. So in those 3D point cloud priors, how do you detect stuff very, very quickly? And this, for example, is a system that runs on the car that looks at vehicles on motorways. The same system looks at sort of people in crowds, same sort of idea. And because how we did it, and this is about, this is just under a year old, but because how we did it, it was state of the art. It kind of was about twice as accurate and about 10, 15 times as fast as the previous state of the art. So we do this in 3D, but of course we also do this in 2D. And now this should not be surprising to really anybody, right? So by now you can download stuff from the internet that does something like that. Okay, so that's neat, fine. Oh, and of course we can look at traffic lights and try to interpret those, right? Clearly a thing that's crucial. So the color of the traffic light changes with the state of the traffic light. But what about this? What about this experience paradigm? Because in the perception side, many people could have shown you these videos, right? Not quite as good, but hey, could have shown you those videos. But what about experience? So many people here may have heard about the sort of action perception loop. Clearly, perception helps us act, or helps our machines act. Clearly, we can act in order to aid perception. We can act to make perception better. That's a really well-known thing. It turns out there's also such a thing as a navigation perception loop, and that's not such a well-known thing at all. And so clearly, perceiving the world allows us to navigate. But it turns out that knowing something about where we are, navigation, can really help us in our perception. Sounds a bit cryptic. Okay, so what does that mean? Consider this. Consider you want to detect pedestrians and cyclists in Oxford. Okay, so here's how that works. You will go to your group member or your PhD student or someone. You say, this is what I want. Please, at the end of next week, make it work. That person then will go away and will read some stuff about whatever detection frameworks are out there. And whatever data sets are out there. And then what happens is that person, will find your trainings, find a training data set, I don't know, INRIA or, Caltech or ImageNet or whatever, train an object detector, and because he or she will have done a hell of a lot of really high quality reading, they will know that there's such a thing as hard negative mining, right? Where you go, okay, training data set, train your object detector, apply your object detector to the training set, identify any false positives. You can do that because you've got your labels in that data set, right? Store those, feed them back into the training, retrain, repeat. Okay. Note that for that to work, you need labeled training data. Okay. All right. Hold that thought. Because what happens when you dump this thing onto a vehicle is this, right? So you've now trained with some data set, and you dump this onto Oxford. Onto a car in Oxford, and now this result looks like something. So it's been described to me as tantalizing but not convincing, which is something that's very often true when it comes to sort of machine vision, right? Particularly in the kind of less recent days, up to a couple of years ago. So you could look at this and you can go, oh, I can kind of see that something kind of, yeah, but nah, right? Another thing I should say is I'm a little bit unfair here because I only show you the raw detections. There's no tracking through time going on, which is obviously a good thing, but I'm trying to make a point with this, so bear with me. Okay, tantalizing. All right, so why is that? Negatives, knowing what is not a thing, is really important in learning, in machine learning, okay? Very, very important. That's the thing we know. And so if we look at something like the INRIA data set, this is what typical negative images look like. Okay, and they're delightful. I mean, they're the mountain lakes and the ski slopes and a beautiful picture of Barcelona. Great. But now we have to apply some introspection in the literal sense and figure out why we've got these beautiful pictures. Why does the machine not get the fact that many things it flags us up as human are not actually people? And we did some thinking, and then we did some more thinking, and we realized that sadly, there are no ski slopes in Oxford, okay? And that is a problem because it's kind of learned that the things it looks for in negatives are things like mountain lakes and ski slopes, okay? So we don't have any mountain lakes or ski slopes, sad face, but we do have these things. We've got these pretty good 3D priors of what the world looks like. And that's a really useful thing because it allows you to do a bunch of sort of heuristic checks, right? So for example, you could say, well, if my image is here, and this is sort of the bounding box that my detector spits out, that I can reason about where this sort of thing sits in terms of the ground plane. And because I can do that, I can say, okay, well, actually, I can also make a height assumption. Say, a person has to be taller than 2 centimeters in all likelihood. Okay, and you can say, well, actually, so this looks like a sensible sort of idea of what a person might be, just based on those 2 checks. Note, though, that knowing where you are really helps here, because in order to apply those checks properly, you need to know where you are so you can register or localize into that point cloud. Okay. So in this case, this is what a deployment model would look like. So you get your image data feed, you get your object detector, you run that thing, you run this sort of scene filter, we call it the sanity checker, and then you output detections. That's what everybody does, okay? That's not particular to us. Now we actually feed pose into this as well, knowing where you are in the world. And you basically throw out all the stuff that you decide not to use into some memory, okay? You stick that back into your place-dependent database, you retrain, and you get back to your object detector. And for those of you who are keen and have listened for the past, I don't know, 3 minutes or 4 minutes, this now looks very much like the hard negative mining loop with the labeled dataset previously, right? It's just that this is basically free. There are no labels required, okay? And this is what we call experience-based classification. Now, what's the effect of this? Why is that a cool thing? Because when you train your object detector, which you've trained really well, but it really doesn't work that well, right? You dump it onto the car, and you use your sort of heuristics to say, well, this stuff really isn't something. But it's not you saying it. It's the vehicle that figures this out, right? It's completely self-supervised. So that's day 1. And then you go out on day 2, and you go, okay, well, this looks better, but there's still some stuff happening, here and there, which shouldn't really be flying through the air, unlikely to be a person. Useful thing. And then you go out the next day, and note that all you're doing here is drive. Nobody clicks on anything, right? You don't point at stuff. You literally just get in the car and you drive. Really important. And all of a sudden, you can believe that more useful things are happening. And after day 5 or so, this stuff looks more than tantalizing. And again, I'm not showing you any of the tracks. I'm just showing you the raw object detections, so you can get a sense for how the raw object detector has improved. So you can look at this, and I hope you'll agree with me, but you can look at this and you can go, oh, I can see how this can now actually be a useful thing. What's more, it's completely self-supervised. And it's done this by sort of quietly in the background observing how you drive without you actually interacting with anything. And that's a really important thing. And it's important to me because that's what I really care about. I would like you to just use your machine, whatever that is for that matter, and I'd like it to get better at doing what it needs to do in order to make your life better. Really important thing. Okay, I've talked about experiences a lot. This is an elaborate, very, very old experience, and I'm just going to talk about this briefly to highlight a thing. So these points here, the white stuff, are these point cloud priors. Everything that's colored are things that are annotated, like lane boundaries, lane driving directions, that sort of stuff. And most, if not all, autonomous driving projects require this sort of map. We call it a semantic map, right? A semantically annotated sort of prior map. Now, I've already talked to you about all these amazing sort of machine learning techniques that we've got, and the detectors that we've got, and these capabilities that we've got. How do you think we can come up with this? It would be inferred from experience. Right, okay. So that's a really good idea. You could absolutely infer it from the experience, but actually we don't. A lot of that stuff is hand annotated. Question to you, why is that? Exactly right. Sorry, I can't see who actually said that. Yes, you. Because this stuff is really important. If you get that wrong, really bad things happen, okay? And that's a really interesting challenge for machine learning, and I think we should pause here. If we're all machine learning enthusiasts, clearly, let's pause here for a minute, and let's think about what's really important about this? It's knowing what you don't know, right? And people are really good at this. People are really, really good at saying, this could be this, but I'm not quite sure. Machines are really bad at it. And that's something that should get a lot of attention in terms of driving this technology forward. Yes? Sorry, I can't actually hear you. Sorry.
We've got a great deal more experience at it.
I didn't pass that. Sorry.
Really?
No, I heard something, but it kind of was.
People have a lot
Yes.
more experience.
Yes, that is true. They do have a lot more experience, and so that's like saying a lot more data is required, for example. In many ways, machine learning, that's kind of a truism, right? So you can easily say a lot more data makes everything better, and I think to some degree that is absolutely true, but there's a different way of thinking about this. One is that as machine learning enthusiasts, as applied machine learners, as theoretical machine learners, we should spend some time on figuring out what it is that makes these systems often overconfident and what we can do about this. So we had a track of research, a thread of research that I'm not really going to talk about much, that was literally called introspection, right? And that looked at the machinery that you use for detecting things, for classifying things, and said, well, what is it that gives us confidence values, and how are they moderated by the framework itself in order to be in any way useful to you? That's one thread. The other thread, of course, is looking at the input data, right? So say, does this data look anything like what my system can handle and has handled before successfully in some way? And bringing that into sort of an experience paradigm, exactly right. I would love to do that, and that's something we're going to do looking into the future, absolutely. But yeah, so data and experience is a big deal. Until then, though, I'd like to make really efficient use of the user, right? And so one way of doing that is active learning, whereby we say, okay, well, we have a system where somebody who's not trained in any of the machine learning techniques can just go, okay, well, today I'm interested in, this happens to be an overhead image of car parks because it's part of this V-Charge project, which was about cars parking and charging themselves. And today you might be interested in car parks, tomorrow it might be fire extinguishers. But the idea is that you provide a few examples and then you click on learn and it just goes, pfft. So given that you were interested in these things, you may also be interested in all these other things. And you kind of go through an iterative process with that. And that's sort of a useful thing because that means that it's a very intuitive way of interacting with a system like that. And ultimately, with a very few iterations, you end up with a system that has learned everything about car parks in your environment, everything about, I don't know, fire extinguishers, or we've got some of this stuff running in different environments where it's, you know, different things become important at different points in time. Important thing here, though, is that, again, this is suddenly very workspace specific. Experience-based classification, what I just talked about, also is very, very environment specific. So in terms of philosophy of technology, this very much is about developing tech that embeds itself into a workspace, into its own workspace where it's deployed, and becomes really expert at performing there. And the price we pay for it, that it might be just a little bit crap everywhere else. But that's okay, because actually it's unlikely that my car suddenly has to work both in central Oxford and in central Tokyo, right? That's an interesting thing. I'll leave that bit with you. Okay. One last thing, because I can, is this. So we hear a lot about deep learning. Fine. We don't really want to talk about deep learning too much now, because it will take a long, long time. But there is this idea, there is this vision of what happens, could we just dump a sensor into the real world and walk away and have it learn to somehow interpret the world in some form of meaningful way? And the answer is sort of not through any sort of magic, but the answer is yes, we can, if we formulate the problem right. So I would like you to imagine the following thing. This is a sort of a busy Oxford road junction, right? Pedestrians, buses, there's like pedestrian zone, buses, taxis, bikes, all that sort of stuff. And imagine you basically plonk a 2D laser scanner that scans like this, right, into the world. And so it kind of touches all of these things, according to the red lines, for those of you in the front. And you walk away, and what you would like to get out just from the sensor observing the occluded scene, because obviously as you walk past, the laser won't be able to see what's behind you, right? Just from learning about this occluded scene, or observing this occluded scene, you would like to, in the first instance, learn something about the whole world as it is unoccluded. So the whole scene, including what's going on in the occlusion. So that's kind of a way of tracking, which is why we call this thing deep tracking, right? So that's the first thing you would like to learn. And it turns out you can absolutely do that. So what you will see in a minute over here is that the laser's kind of situated up here, and then it kind of points down here, and this is sort of the scanning plane. And as you see occlusions, forget for a second about what the colors mean, but as you see occlusions in a minute, you will see that things keep moving through the occlusions. Okay, and that's a pretty useful thing. Why? Because in this particular case, we didn't have to write down any models. There's no model in there that says this is the kind of thing that an object should do in the occlusion. This is how it should move. This is even what an object is. Any of that stuff. We do none of these things. The other thing you might notice is that when something gets occluded lots, like by this bus, right? So that all of this is in the shadow. It kind of there's a little cloud burst, right, of things that suddenly disappear, and that's essentially the equivalent of a multi-hypothesis tracker, right? It's saying, I've not seen this thing for so long, it's the probability mass of it being in this place is kind of diffusing, right? It could be anywhere in these places now, and that's something that we see. Now, the other interesting thing is that I can't for any amount of time claim that this is how humans do it, clearly, because I have no idea, right? I don't really know anyone who does, for that matter, but there is this idea of making efficient use of what you've learned about the world, okay? So there's an argument that I could make that because I've looked at this data lots, I've kind of learned how to interpret it, right? And it should be easier for me to say, oh, well, this is a human, this is a bike, this is whatever, right? Because I've looked at it lots, I've kind of learned this internal representation of the world. And that should probably be easier than for somebody who just has seen individual annotations of bikes and cars and buses and whatever, to go, oh yeah, that's a bike, that's a car, that's whatever, right? And we kind of see that effect here as well through a process called inductive transfer, and that's a thing that personally I'm quite excited about, right? So what happened here is the colors clearly indicate what these things are. So green are pedestrians, red are sort of stationary things like buildings, blue things are vehicles, buses, that sort of stuff. And the thing that's special about this is that you can absolutely train a system, even a deep network, to do this from scratch. The problem is you need heaps and heaps and heaps and heaps of training data, which in this case is supervised, because you just tell it what's a car, what's a pedestrian, etc. Right? In this case, what happened was that it first learned how to interpret the world in this sort of deep tracking sense. And then we gave it a very modest number of supervisory inputs, like this is a person, this is a car, this is a cyclist. Very, very modest. And it learned to really efficiently make use of that data based on the underlying representation that it had already learned to actually generalize to this thing. And that's quite exciting. So if you tried the same thing with the same amount of data, you would get something that's vastly inferior. Okay, that's just a teaser for conversation later. Point is, perception is tricky. Okay, it's a hard thing. And very often it's limited. Very often it's limited by how we've learned to interpret the world. It's like how we interpret the world is based on what we know, okay? Turns out this toad has no idea about smartphones. But it's okay, because it gets the same stuff, okay? So don't be fooled. Don't be fooled by the fact that you can do a thing. It's actually pretty hard, okay? All right. Bunch of conclusions, don't really care about them. There's a thing that I care a lot more about, which is the following. Why else might this be useful? So if you thought that you've just been listening to a talk about autonomous driving, yeah, kind of, but that's like an eighth of why this is interesting, okay? So same technology we can use for something like logistics and city planning. You probably got a sense for that, right? Having something where you can figure out how far things are away from each other are really, really important in that sort of context. Looking for potholes. Don't get hung up on the potholes. Get hung up on infrastructure management, right? Cracks in buildings, cracks in bridges. Imagine a little box, like we tend to talk a lot about form factors. All this tech we can we can drape over a car, or we can fit into sort of a little box. Imagine every dust cart, in London having one of those box fitted because they're really cheap. All the data that you get and all the feedback that you get about what needs maintenance and scheduling when it might need maintenance. Asset detection. So, instead of getting rid of the cars, what if you wanted to know where all the cars are? And at this point, I have to hold up my hand and say I had nothing to do with any of the autonomous sort of car parking fine vans that go around. Just saying. Same thing, but on the railways. So we've got some of our tech, same stuff, important, same stuff, is on train lines in trials. to basically do asset management along train lines, localize where you are along the train line, and find different things that might be important, and report back. So here, people detection, for example, on platforms, and by the way, a guy on track, which was surprising to everyone. But I think Network Rail spends something like £50 million a year on not knowing where stuff is. This is where I regret this got recorded. Anyway, so that's an important bit. Warehouse analytics, really big deal. So the tech that we've got doesn't need GPS, works inside, works outside. So what we can do is just dump our stuff and drape it over the form factor forklift. Okay, drive it through a warehouse like this, and there you go. You've got a centimeter accurate survey of your warehouse. But also you can localize with respect to it, and do many, many other things, which turn out to be very, very useful. Already mentioned Mars, but autonomous science discovery is a really big deal. Turns out that right now nobody really knows whether a Martian has just performed a dance right next to the Mars rover or not, because we only look at certain points in time when it does a certain thing. So figuring out autonomously what kind of things are actually interesting and worth science is a really interesting problem. Energy management, of course, on Mars, where else, is important in terms of we can figure out when we can switch our perception system off, for example, because we have some form of leeway as to how we can move through the world. But why restrict ourselves to Mars? Why not bring it back to Earth? So does anybody here drive an electric car? No. Okay. So does anybody here know what range anxiety is? Clearly not. Okay. So if you're like me and you break out into sweat every time your sort of fuel light comes on, right? Imagine that EV drivers are typically in that state of mind always. Okay. And it turns out there are lots and lots of interesting things, which will be touched on in the next talk, I guess, which very much iterate over learning again from demonstration. So you can learn how a driver drives and come up with something that becomes specific to the driver, right? So we call this an attainability map, right? Where you can say, well, actually, this is the probability of how far you will get with your current state of charge for you. And when you drive this thing off the forecourt, it'll look the same for all of us. But because it learns how you drive, it will customize itself or wrap itself around you, the user, in a sort of non-obtrusive way. So that's quite neat. But again, it's the same sort of technology. So really, it's about robust lifelong autonomy, right? That's sort of the aspiration of the group. Not just this autonomous driving malarkey, but this. And the philosophy that we apply here is machines that get better through use forever, really important, by learning from demonstration in the wider sort of sense. But in a manner that's entirely transparent to the user. That's really powerful, I think. And of course, while I have the pleasure standing here and telling you all this stuff, it's a massive team effort. This is like an old group photo. There's now about 45, 50 of us that do all this work. It's a super fun environment. So if you have an Oxford, stop by. And that's it. So I think I've basically just about used up my time. So thank you very much.
Testing. Hello. Okay. I just wanted to ask a quick question. You said that you're using perception for classification and you integrating the previous experience or the negative examples in your database in order to improve your classification in your false positive rate. So, but are you also using the positive examples that were theoretically labeled correctly as well, integrated in your database?
So the answer is yes.
Okay. This would be similar to what, I don't know, tracking, learning, detection, Zenedek Cloud does, more or less, right?
Right. So this is the thing that you mentioned, the kind of interaction between the tracker and the detector is a really, really interesting thing. So we're also exploiting that. The problem that you have is that this, so we call this positive mining as opposed to hard negative mining, right? So positive mining is tricky because to do it well, you kind of already solve that problem. So if you could do it well, you already have a detector, right? So negatives, dealing with negatives can be a lot more loose in the sense that you need some heuristics. So if it flies through the air, it's unlikely to be a human.
Yep.
But just because it's on the ground doesn't mean it is a human.
Yep.
Right? So it's got that flavor. The problem that you have with both of these cases is that if you get it wrong, you will pay the penalty of semantic drift, right? So your classes will sort of disperse, and you will get really bad at everything. Now that is something that we still need to develop a mechanism for. I don't really care so much about guarding against it, but I certainly would like to detect that it's happened.
Right. Just one more question about
Sure.
because you're using also you're doing mapping as well, and you're doing place recognition or loop closure recognition in this case. Are you using GraphSlam or are you using different filtering approach to do the mapping?
Yeah, okay. So we don't actually use SLAM, which is a bit surprising coming from our group. SLAM, I think, so I've never really worked in SLAM. This is all entirely sort of Paul's domain.
So it's just basically just odometry, just pure odometry. There's no optimization after the odometry is received or computed from the data.
It's not just real odometry, it's visual odometry.
Yes.
But there is no such thing in our world as a globally metrically consistent map. And we can now have a conversation about why that is a good thing.
Oh.
And you may well disagree, but it's true.
Cool. Right. Interesting. Okay.
All right.
Thank you.
There's someone in the back there.
Just want to ask about the point cloud. Is it available for academic research?
The answer is yes. So the guys are about to publish a data set which is many tens of kilometers of full data. So that's coming out almost imminently.
All right. So can we register for if we want to use it?
Yeah, so if you keep a look on the website, the Mobile Robotics Group website, there will be an announcement there. So we've just announced it to the community at one of the largest robotics conferences in Stockholm this year, at ICRA. And so this will be coming out very shortly for you to download. It's many data packets, which you can download bit by bit. So yes, absolutely.
Do you need very vast amounts of memory to store your experience databases, or do you have a really good way of compressing things into them, or some trade-off? Or?
That's a really good question. So the answer is right now we don't actually compress it, and that is something that we will need to look at. But in terms of memory, how memory intensive this is, it's nowhere near as much as people might think. It's certainly not anywhere near sort of forbidding in terms of the approach, which is a really reassuring way. There's actually a really interesting research question to be asked about how you sub-select the data that you keep in sort of a deployment scenario, and some of the things that we are doing in the context of Gateway and Autodrive kind of leads us down that path, because clearly we can't keep everything. Yeah.
What kind of algorithms were you using to analyze that data? Was it deep learning?
Depends on which part. So the vast majority of what I just talked about, and there was lots, was not deep learning. There were two parts that I talked about that actually that were based on sort of deep architectures. Yes, there was the deep tracking and the bit that I kind of skimmed over, which is the deep teach and repeat. Why do you ask? Microphone's gone. Okay, you can answer later, it's fine.
With the inductive transfer, I might not have got that right, but the what I thought was the inductive transfer bit, I wasn't really clear how that worked, and I was wondering whether there are any papers or whether that was published work that I could look into in a bit more detail.
Yes. So anything that talks about multitask learning will point you in that direction. Really worth looking at. I think it's one of the most exciting bits of what we do right now.
Maybe one more question.
If your car is learning from you, what happens if you're a really bad driver?
Then you really don't want to be sharing your experiences. What happens if you're a really bad driver? So that depends. It depends how the experiences are distributed, right? And what actually happens with that sort of information. So you could, for example, envision a world where in order to get insurance for your autonomous car, your car needs to pass a bunch of virtual tests, right? And so that could be the place where that gets filtered out. You could imagine that in a world where everybody shares experiences, customers somehow get to vote about, or there's some form of feedback as to how happy you were with those experiences, right? You could envision a world like that, so that might be a way of filtering it out. There is also the evolutionary aspect that might say, if you're a bad driver, your bad experiences will filter themselves out by themselves, right? I don't necessarily subscribe to that, but we can talk about that. There are ways of solving that problem.
All right. In any case, I'll just thank Ingmar for coming down.
London Machine Learning Meetup.